take a look at an example problem. A torsion spring similar to that shown in figure 1611 is made of 0.05-inch diameter music wire and has 6 coils in the body of the spring and straight ends. Distance A is 2 inches. The outside diameter of the coil is 0.654. If the maximum stress is set equal to the yield strength of the wire, what's the corresponding moment? In other words, what moment causes the wire to yield? B, with load applied, what is the angular deflection? And when the spring is loaded, what is the resulting inside diameter and what size bar should be used inside of the spring? Stuff we just talked about at the end. The picture is given there as well. So mean coil diameter, as before, is equal to the outer diameter minus 1 wire diameter, or 0.599. Inside diameter is equal to mean coil diameter minus another wire diameter, 0.544. C over D is 10.89. That's the value of C. We use that in the equation Ki, which I have now erased, but that's the equation for the stress concentration due to curvature, 1.074. Tensile strength, as before, these values are in the table, and I'm taking Sy equal to 0.6 of SUT. That's actually a little low. We could take it at higher than that as well. So remember that we have an equation that says sigma, I erased it. Okay, so that equation says sigma is equal to Ki 32m divided by pi d cubed. That's your usual bending equation. So it says what value of the moment creates yield strength? Substitute Sy here, solve for m, which will give you that equation. Pi d cubed Sy over 32 EI. That's where it comes from. All of the values are known. That's how much moment you require. Number of active coils is number of coils in the body plus number of coils at the end. Number of coils in the body is 6. Coils at the end, 2 inches apiece on each side. So 4 divided by 3 pi dn, 6.71. Again, a little bit of note there as well. K theta, this equation. Again, everything is known, gives you the spring constant. And at sigma equal to Sy, it says what is the angle of revolution? That's m equal to k sub. This is not k times theta, it's k sub theta. It's just, the subscript is just to show that this is not a linear spring constant, but a rotational spring constant. That's all. If you want to use k prime or something, that's fine too. So 0.432. So the total number of coils has been increased by this value, 0.432. So, oops. Did it again. So the total number of coils is now the original number of coils, 6.71, plus the rotational number that is introduced by the number of revolutions, 7.142. The resulting inner diameter, according to the equation I just wrote on the board, is 0.511. So you can put a 1/2-inch diameter mandrel through there. And you will have some tolerance there. Any questions? Yes.
part A, you said Sy is equal to 0.6 SUT. I thought you said the range before was 0.3 to 0.5.
That's for torsion. This is bending. And that's why I said it's low. Even at 0.6, it's probably 0.7, 0.75 is a better number than 0.6.
Where was that information again?
Which information?
That scale factor in the book.
It depends on the type of material you have. For high strength materials, the yield and tensile strength are closer to one another. That's why I'm saying 0.6 is low, because we usually use high strength materials for springs. For low strength material, the yield strength is farther apart from the tensile strength. And remember that as you get to a higher strength material and yield and tensile strength get closer, it's because the material is becoming more brittle. And therefore, from the time it yields to the time it breaks, not that much. So that's where it comes from. It's an estimate, of course. It's an estimate. It's not an exact value. Again, if you are working with a specific material, you should use properties of that material rather than an estimate. Okay?
So
You have a question? Yeah.
yield strength.
Sorry?
You would just tell us.
Oh, no. I'll tell you that. No. I'm not going to have some of you use 0.5, some 0.8, some 0.6. That means I'll have to solve 20 different problems.
For that shaft that goes inside the torsion string to keep it stable, does it have to be touching the spring to do its job?
No, it shouldn't be touching it.
It shouldn't be?
No, because as the spring moves, it will rub against it and it will be worn off.
So it's just there to make sure that the spring doesn't come off loose entirely, not that it stays exactly.
Correct. You just want to make sure that it stays put, but in reality, it shouldn't be touching the spring. No. Anything else? Okay, the final. I guess we're done with the taping. The under bending, so this is the same thing. So the length of the spring, I'll write it here. L equals pi d n, the circumference of one coil multiplied by the number of coils. Now, right now, some of you may be thinking, what are you going to do with this? That's not a coil. We will use an equivalent number of coils for those two pieces. They are also under bending. They must be included in that equation. So yes, we have so many coils here. We'll find an equivalent, or we'll give you an equivalent. We don't find it. You can't. We don't prove it here. We'll give you an equivalent number of coils for that. And that way we'll take care of the whole thing. So I'll write that in just a second. So this is 2 pi dn. And if you integrate that and solve for theta, this is what you get. So integrate this, put in the limits, solve for theta. Theta is equal to Fr over EI pi dn is equal to 64 Fr dn divided by d to the fourth E. That's the angle of rotation. Notice that we have defined the spring constant, K, as the moment divided by the angle of rotation. So here's the moment. There's the angle of deflection. And if I divide those two, I will get the spring constant. Therefore, K equals m over theta. M is the same as Fr. And that will give you d to the fourth E divided by 64 dn Now, this is theoretical. In actual practice, there is, since these coils are touching one another, as you just saw, in actual practice they rub against one another. And therefore, some friction is produced here. That reduces that, the internal energy. Therefore, it affects the spring constant. To take that into consideration, well, actually, first we would like to define it. I'll talk about taking that into consideration. But before I do that, because I don't have the equation for that outright, before I do that, let's say what is the unit for this K? Moment per radian, that's right. So pound inch per radian. And usually per radians we don't say, it's pound inch. Newton meters, Newton millimeters, whatever. Because remember, this is in radians because I wrote that equation. That's only true if theta is in radians. It's not true if it's in rotations or degrees or anything like that. We, as I said before, we generally define this in terms of number of rotations. So if this is per radian, if I multiply it by 2 pi, I will get K for 1 full rotation. This is K for 1 radian. That's it. If I want 2 pi radians, got to multiply it by 2 pi. So K will be equal to, we have called this K prime, I guess, for 1 revolution, 2 pi times that. 2 pi d to the 4th E divided by 64 dN, which is equal to d to the 4th E divided by 10.2 dN. And this is still theoretical. I have not taken into consideration friction between coils. If we bring that into consideration, this is more like d to the 4th E divided by 10.8 dN. Considering coil friction. Any questions? So that's the spring constant for coil springs. So let's just say this is K prime per revolution, because you multiply it by 2 pi. One more thing that happens when you have coil springs, that usually a mandrel fits inside the spring to keep it in place. When you apply a load, and I shouldn't have erased that, when you apply a load F here, the spring rotates, right? Deforms by rotation. So the number of coils increases. If you started with 1 coil, maybe it's now 1.5 coils, 1.25 coils, what have you. As that happens, the internal diameter of the spring also decreases, becomes smaller. So if you have a mandrel here, you got to make sure that that diameter, the internal diameter, the inner diameter of the spring, does not become so small that it actually touches the mandrel. In order to do that, you must be able to find the internal diameter of the spring after load from the internal diameter of the spring before load, and the load, of course, or the number of coils. There is an equation that will give you that. And that is this equation. di prime is equal to n over n prime di. In this equation, n is the number of coils before load. Di is inner diameter before load. N prime is number of coils after load. And di prime is the inner diameter after load. So, once you find how much it has rotated, 1 revolution, 2 revolution, half a revolution, a quarter of a revolution, you know how many coils you've added. The only thing that remains here is this question we haven't addressed yet. What are we going to do with this? Or the one on the other side. We will convert them to equivalent number of coils using this equation. And end equals L1 plus L2 divided by 3 pi d. This is L1 and this is L2, in case you have them on both sides. Therefore, the magnitude of n in this equation, in all of these equations, is equal to n body plus n end. And now you can use these equations and find all of the values. Any questions? Ooh. Yes?
So if one of those arms is resting against a support, it still carries the load, right? Or
No, it doesn't.
So
It's like a
dead coil?
dead coil, yes. Because remember that if it's sitting against a wall like this, there's no way it can bend. If it doesn't bend, it's not carrying any load. So if I had it like this,
Yeah.
L2 would be 0.
So then the end would just be L1 over.
Correct. And compression springs. And that tension springs are wound shut. And in order to change the length of the spring, you first need to overcome a compressive preload that's inherent in the spring. In other words, the coils are pressing against one another. You have to overcome that and then apply load. That will change the length of the spring. So, if you draw the force deflection diagram for a tension spring, starting from 0, you keep putting in forces and nothing will happen until you overcome the initial preload in the tension spring. After that, the relationship will be linear like that. So F is not equal to Kx. F equals Fi plus Kx, the initial preload. You have to add that in. Any questions? So next, yes?
So there's a compressive preload in that, or in the spring?
Sorry?
The preload is compressive in the spring?
It is a compressive load because you're applying a tensile load, right?
How
To overcome that.
how would they do that in the spring?
If you take, they just take a piece of rope and twist it like this. It will get round over itself and it becomes shorter. Now, of course, a rope is a very flexible material, and you probably won't see any compression between loops of a rope. But if you're looking at a stiff material such as steel, you twist that, that's going to roll, and they are going to be pressed against one another. Oh, by the way, my office hours for next week: Tuesday 10 to 10:50, and Wednesday 10 to 12, basically 10 to 11:50. Now, torsional springs. Well, I had this picture here too. Could have shown you that. But that's all of the stuff on tension springs that we just talked about. Tables 10.7 and 10.8 give you allowable stresses for tension springs, very similar to those we had for compression springs. One for static loading, 10.7, and the other one for cyclic loading, 10.8. But they're very similar to the tables that we had for compression springs. So torsional springs. Torsional springs, as the name implies, are in torsion. Are compressive springs in compression? No. Torsional springs are not in torsion either. Torsional springs are in bending. They carry the load by bending. The reason why they're called torsional spring is that they create a moment. A moment is required to deform the spring. So if you take a look at a torsional spring like this, many coils like that, then ends have to be something similar to what I have on the board so that you can apply a load here, a load F. And that load F produces bending in the whole spring. And therefore, your stresses are normal stresses. As always, there's a curvature of the wire that produces a stress concentration factor. In this case, that stress concentration factor, I guess I've erased the other one, so I'll write this one. Similar to the other one we had before. Ki, this is at the internal surface. That's where stresses increase. They decrease on the external surface. 4c squared minus c minus 1 divided by 4c times c minus 1. And c, once again, as before, is 2 call it Ri. 2Ri over d. If I call this distance r, then the moment that's generated in here is F times r on that spring. The stresses are calculated as before, writing, of course, a bending moment equation. So sigma is equal to Ki 32m divided by pi d cubed, which is Ki times 32 Fr divided by pi d cubed. The reason why I wrote it Fr because I'm going to use it. Otherwise, you don't have to use it. You don't have to look at it in the second way. We also need to define the spring rate. For torsional springs, how is the spring rate defined? Moment over rotation, that's right. And you can define it as moment per radian, that's rotation. I would not suggest moments per degrees, but theoretically, if you want to define it that way, you can. A better way to define it, moment per revolution. In order to do that, we need to find the spring constant. And that spring constant is defined like that. The ratio of the moment and the rotational angle. Similar to what we did for compression springs, in order to do that, we use Castigliano's theorem. According to Castigliano's theorem, the strain energy stored in a material under bending is equal to the integral of m squared dx divided by 2EI. That's a material in bending. And m, in our case, is equal to F times R. F times R. So if I substitute that in here, you get this is equal to F squared R squared dx divided by 2EI. If I take the partial derivative of the strain energy with respect to the force F, assuming this part doesn't move, let's say it's against a flat plate or something like that, I will find that distance. Correct? According to Castigliano's theorem, the partial of the strain energy with respect to the force is equal to the deformation at the point of application of the force and in the direction of application of the force. So that's what I will find. The angle of rotation here is theta. So let me draw that a little bit larger here. So this is the spring, the initial shape, the final shape, that's delta, that's theta, and that's R. And R times theta will give you delta. So delta equals R theta equals the partial of the strain energy with respect to the force F. And we take that partial by going into this integral. So that'll be equal to the integral of partial with respect to f would be f r squared dx divided by EI. Going from 0 to what's under bending? The whole spring is under bending, right? Yeah. The whole spring. Therefore, the length should be the length of that spring if you unwind it. Remember, that's how we came up with this equation. It was straight beam. A couple of things. Number one, on these equations that I wrote here, this is not C equal to D over D. This is just a constant. Call it C sub C. I don't know, constant C or something. This is not D over D. It's either a half or a quarter depending on the end conditions of the two that I gave you. That's number one. Number two, insofar as the spring constant is concerned, if you run an experiment, your points look like this. But this is 0, 0, and that's the solid height. Oh, sorry, solid force, which gives you the solid height. So this would be delta at solid length. They are nice and linear here in the middle. Not very good when the loads are very small. Not very good when the loads are near the solid length of the spring. So generally, when we want to find the spring constant, we ignore this part, we ignore that part, and base everything in the middle 75%. And that's why you should always calculate the spring constant as the change of force divided by the change of deflection, rather than just simply force divided by deflection. Because in many instances, if you put a good line through these points, it won't pass through the origin. If you put a line through the experimental points, it won't pass through the origin. But the slope is the spring constant.
I had a real quick question going back to surge and resonance in the springs. Is the reason that that's important to look at because we're using such small factors of safeties? Like if we were using a larger factor of safety, would the resonance not be as important to the design?
Resonance is always important if it happens, whether you have a large factor of safety or a small factor of safety. And remember that if you use a large factor of safety, and you do that by increasing the wire diameter, then you're going to increase the weight. And if you increase the weight, you decrease the natural frequency of the spring, whereby we want it to be 15 to 20 times that of the applied load. Now you're going to reduce it to something less than that.
Right.
So the two do not go in the same direction. So just having a larger factor of safety doesn't mean surge is not going to occur.
Okay.
In fact, they go in the opposite direction.
Yeah, I guess my question was that if you had a larger factor of safety, would the surge be less important because
No.
the spring can handle
No,
it?
they have nothing to do with one another.
Okay.
One is, although they're both related to the geometry of the spring, other than that, there is no relation between them. You must always check for surge. Okay? Tension springs. As you saw with the samples that I sent around, these are springs that are wound essentially shut. Oops, wrong stuff. And in order to apply a load to them, you have to have ends that are hooked or are otherwise capable of carrying a load. Therefore, so similar to what you see there, the curvature of the wire is actually a double curvature. There's a, and this one is probably the better one to look at. There's a curvature here, right? Right over here, there. See that? That curvature is shown here. Agreed? That's one curvature. There's another curvature over here. So this thing curved like this, and then it twists like that. It's a double curvature. And you have to check other factors than the shear stress in the body of the spring. For example, schematically, if this is your tension spring, and you apply a load here, F, well, that section is under bending. So you need to worry about the bending of that section as well. It is also curved, so it's a curved beam. And we generally use a stress concentration factor to take care of the curvature, and this is no exception, and we'll do that. So this creates bending here. What does this other curvature down in here create? Maybe this is a better picture. The curvature here. There's one curvature here shown behind this. There's this other curvature, which is right there. What kind of stresses does that produce when you apply a load?
Shear.
Shear, torsional, right? This is very similar to, I don't know whether I mentioned this last time in this class or not. If you have a garden hose, and you, did I talk about that? You coil the, if you have a garden hose, regular or run-of-the-mill garden hose, they usually have a line on them along the length of the hose. And you put this circularly, very nice and neat on the ground, and just pick up the end and pull it up. Basically, that's what you're doing. And if you do that, you see that that line that's on the hose twists, which means that that hose is in torsion. So we need to worry about the bending and torsion of the hook as well. Aside from the fact that, of course, the length of the spring is going to be the body length plus 2 hook lengths. That is sort of self-explanatory, if you will. The stress concentration factors that are used for bending and torsion are, so I'll say, for example, point A here and point B here. For point A, the bending stress concentration factor is 4C1 squared minus C1 minus 1 divided by 4C1 times C1 minus 1. And for B, write this as K bending so that you don't confuse it with KB, the Berger-Strasser constant. So this is K, I guess, torsion or shear, is equal to 4C2 minus 1 divided by 4C2 minus 4, where C1 is equal to 2 times the radius of curvature at A divided by the wire diameter, and C2 is equal to 2 times the radius of curvature at B divided by the wire diameter. And those 2 radii of curvature, of course, are different. If you take a look at section A of the hook, you will see that it is under bending and what else? Torsion? Take a look at section A on that picture that I have. Let's draw a free body diagram. Make a cut here. Draw this part, just that part. Isn't there a force here as well? And a moment, Ft over 2. So that section is under axial load and bending. Therefore, the stress to which you will apply this stress concentration factor for that section will be given. Sigma is equal to K bending times 32 m divided by pi d cubed plus 4f divided by pi d squared. And m, of course, is Ft over 2. This is m. And if you put the value of m in there, not much will happen to it. You can just take the value of f out and you'll end up with this. K bending times 16d divided by pi d cubed plus 4 divided by pi d squared, all times f. It's just factoring out some value there. For shear, tau max, K shear, and 8fd divided by pi d cubed. We've had that before. So that's the difference between the two. Other than that, in the body of the spring, all equations that we use for compression springs are valid for tension springs. All that has happened is that the direction of the load has changed. That's it. Everything else remains the same. There is one difference, one more difference between tension springs. Mean. So if you get nice ratios like this, don't calculate them both. Just calculate one and use the ratio. I don't know whether I haven't done that here. Well, actually, I said 3 tau A. There we go. Tau A is calculated 143. If Fm is 3 times Fa, it follows that time is 3 times tau A. So 430. In other words, you don't need to recalculate that again. SSE 465 MPa, assuming peened wire. And again, I'm using the approximate values that I gave you here. SSU 0.67 SUT, 935. Once again, the Goodman line, the equation of the Goodman line. Equation of the load line. Solve them together, get SSA. And as before, divide that by tau A to get the factor of safety. So to summarize, we're a little bit, we have a little bit of leeway here on the factor of safety as well. And this is the summary of the design of the spring. Except for the surge, everything else is fine. You might want to change it just to take care of that. Any questions?
Can you explain really quick physically what the surge means? Like,
I'm sorry?
what's physically happening with the surge?
The deflection of the spring will get unduly high and it breaks.
Resonance, I'm guessing?
It's resonance, basically. That's what it is. It's exactly the same as what we had in shafts. In shafts, the deflections got unduly high. Here, that was bending deflection. Here is compressive deflection. The deformations will get unduly high, which means that you will either reach the solid height or you break the spring. One of the two. And neither of which, of course, is desirable. Okay, anything else? Okay, please take a shorter break if at all possible, maybe about 5-6 minutes or so, so that I make sure I have enough time to do not just the course, but some of the administrative parts of the course as well. And then I'll talk about the final two when you come back. Correctly, they're really giving you the spring constant without saying they're giving you the spring constant. They're saying the load varies between 300 and 600 as the spring length varies over a range of 25 millimeters. So 300 divided by 25 is your spring constant. Now you don't have to go to d to the 4th g and all of those guys to find the spring constant. So let's take a look and see how you would design this. First, is infinite life required? 650 RPM, you get to 1,000,000 cycles in 26 hours. So apparently you would like to have infinite life on this thing. Assume a value of c equal to 8. This is a good mid-range value. And a wire diameter of 5 millimeters. And the material is given, of course, in this one, so we'll use that. We'll use the valve spring wire. SUT, A is AD to the M. You may find in your books that some of these numbers are a little bit different than what's in the book now. These are numbers from the previous edition. But they are taken from the table in the book. Even if you see the discrepancy, don't be alarmed by that. They are strictly from that table that gives you A and M. If you have a high strength steel, then the yield strength and tensile strength are closer to one another. So in here I'm taking an upper limit on SSY, 0.5 rather than 0.4, 697. Use a small factor of safety to minimize weight. Remember that we would like to make sure that there is no surge, and the equation for frequency is some sort of a constant times the square root of k over m, or kg over w. They're both the same. Therefore, if I would like to be this to be high, I've got to reduce that. To reduce the mass, I need to reduce the wire diameter. If I reduce the wire diameter, my stresses are going to go up. Therefore, my factor of safety can't be too high. That's why in springs we generally use relatively small factors of safety. In this case, I'm using a 1.2 for exceeding tau max. The maximum allowable, therefore, is equal to the strength, in this case the yield strength, 697, divided by 1.2. So I got to make sure that the stresses in the spring don't pass that value. The maximum stress in the spring is produced with the maximum load. So D is 40, there's KB, 1.17. Tau max is equal to KB, 8 FD divided by pi d cubed, 1.17, times all of this. And all of that you have, 572, a little bit less than 581, so we're good. Remember that 581 has the factor of safety included in it already. So that's okay. The spring rate, or the spring constant, is the change in load divided by the change in deflection. And that comes out to be 12 newtons per millimeter. That's the spring constant. And G is 74,000. This is for steel. Therefore, now that I have the value of K, and I have all of the geometry, D&D, with the assumptions that I made, I can find out how many active coils are required. Yes?
Why did you use 300 newtons instead of 600? Find the K.
Why did I use what?
Why did we use 300 newtons instead of 600? Find the spring constant.
Read the problem. Read the problem. If you don't answer your own question, raise your hand again. I think you just answered your question. Okay. So change of load, change of deflection. And then we have K. We find NA. It's squared and ground, so the total number of coils is 10. One dead coil at each end. The free length. The solid length, now that we have the total number of coils, multiply that by 1 wire diameter, you get the solid length. The free length is equal to the solid length plus the deflection at the solid length. That's deflection at the solid length. Now then the question is, if I want to find the deflection at solid length, and I have K, which is the spring constant, I need to know what force should produce the solid length so that I can find the deflection by dividing that force by the spring constant. We get that force from this consideration. The force at solid height should be somewhat larger than that of the maximum force applied. And then we said this, your book says this is 15%. In this case, I've taken it as 10%, just to show you that these can be different. So the force at solid height is 1.1 times the maximum force, which was 600 newtons, given. Therefore, the deflection at solid height is 660 divided by 12. Add that to the solid length, you get 105. That's the free length of the spring. Check buckling. Alpha is 0.5 because this is squared and ground and held between parallel plates. So it's like a fixed column. And alpha is 0.5 for that. Free length divided by mean coil diameter, 1.3 is less than 2.63, so we're good on that. Check surge. Rho is 76 kilonewtons per cubic meter. That's the unit weight of steel. Comes from table A5. And F equals 1/2 times the square root of K over M. This, of course, is the same as the C, in this case, is 1/2. The square root of kg divided by W. And since I have the unit weight and not the density, I need to bring in g. So I'm really using this equation. You might want to write this equation next to the other one. I'm really using that equation with c equal to 1/2 because of the end conditions. So that's K. The mass M, I actually write it as W divided by G. That's G in the metric system, but in millimeters per second squared rather than in meters per second squared. That's the unit weight, gamma, and that's the volume of the spring, volume of the solid part of the spring. You check that and it comes out to be 140 cycles per second. It says the shaft rotates at 625 RPM. That's approximately 10.4 cycles per second. So we're just a little bit shy of that minimum of 15 to 20. I have let it go and not done a calculation, but remember that we still have a little bit of leeway I'm sorry?
I think it's actually 650.
650 what?
RPM, the shaft rotating.
Yes, which is equal to 10.4 cycles per second.
You just made it says 625, so I'm guessing it's like a minor error, or did we reduce the RPM for some reason?
As I've written this, no, I've written this a little bit sloppily. That should be CPS, cycles per second, or hertz.
Yeah, no, my remark isn't about the CPS, it's that the problem describes the rotation of the shaft at 650.
Okay.
And you calculated the CPS for 625, so I'm wondering. Did we
Oh, is it 650?
Yeah.
Oh, I thought it was 625. Well, I should read the statement of the problem carefully, shouldn't I? So it is going to be a bigger issue than it is now, because 650 is going to be somewhat larger than 10.4. For example, 10.8. However, we do have a little bit of leeway in almost everything we've checked. The most critical has been the stress, which were just under the allowable stress. Remember 581 and 572. But there's still a little bit of way. We can reduce the weight. If not, you're just going to have to go to a stronger material. And that way your strength will go up. You don't do anything to the spring, strength will go up. We can reduce the weight, or we can pick another material. Finally, fatigue. This, again, is a repetition of things that we've done many times. KB 1.17, we have it as before. Mean value of the force 450, the alternating value 150. So the alternating is 1/3 of the point. Let me mention this as well, because you'll see this symbol in your book. You may be wondering what it is. When we are designing springs, we would like to make sure that the maximum load on the spring never exceeds the load that will take the spring to the solid height, the solid force. Never exceeds the solid by some factor. Your book chooses a factor approximately around 18% and says that the maximum load on the spring must be less than or equal to 7/8 of the force at solid height. Written differently, and this, you can actually solve this equation. This is the way it will come out. And this is the symbol C that is used in your book. And they say to take this approximately equal to 15%, which is actually the same thing that you have there. This value, this C, is called fractional overrun. Meaning, how much should you increase the maximum load before you get to solid load? That's basically what it means. The 15% or 0.15 is not carved in stone. It is not something that you'll see every place. You may see 10%. It all depends on your design. You may see a little bit more. 15% is just one of the values that's used. So don't think that that's really something that is fixed and a property of the material or anything like that. So this fractional overrun is the amount that you have to increase the maximum load to get to the solid load. In some books, it is also called clash allowance. Clash allowance. So you may see that as well. But your book refers to it as fractional overrun.
Is
Is it always gonna be 0.15?
No, that's what I was just saying.
No, it's
Your
for
book
stable.
says 0.15, which is fine. If you want to use 0.15 is okay. But you will see that in one of the example problems, I'll be using 10%, 0.10.
So it's 0.15 unless it's otherwise.
Yes, yes. Or the problem may tell you. It may tell you the force at solid height should be 12% larger than the maximum load, for example. Then it's neither 10 nor 15, but 12. So, okay. So factor of safety for torsional yielding should be, or for this maximum load should be somewhat higher because it doesn't yield at solid length. So there's no sense in calculating that unless you actually want the number. It's going to be a little bit over the factor of safety that we found. But for 50 times 10 to the 3 cycles, which is what they also ask for, you now need a different. This would be your Goodman line, 10 to the 6. Now you need a different line here. You need that line. So you have to find that value. These values, which we also use in order to find the life or calculate factor of safety for a life other than infinite life. For shear, this, forget the exact number. Let me check here. Yeah, it's over there. I just saw it. If you draw this diagram for shear, this factor was FSUT, remember that? In here, well, actually, let me finish this. And that was SE. For shear, you'll have this shape. They have something exactly similar to that. The value of F, rather than finding it from the graph that you used to find it, and we said most of the time is around 0.8, 0.9, something like that. It's more like 0.7. In fact, in here we're using 0.72. 0.72 SSU. So that's the value of F. The 0.72 that you see is the value of F. And I have a little note here. It says for torsion, the intercept is closer to 0.72 than 0.9 SSU, only for torsion. So your graph will now look like this. This is SSE, and that is FSSU. And this is 10 to the 3 cycles, that's 10 to the 6 cycles. That's the only difference. Other than that, everything is done exactly the same way we did it for normal stresses. SF equals AN to the B, put in your number of cycles here, you find 71.5, and it better be larger than SSE. The two equations, this one, for the strength line, this is not the Goodman line anymore because it's not 10 to the 6. This one for the load line, the same as before. That equation doesn't change, load line doesn't change. Find the intersection and the factor of safety for 50 times 10 to the 3. Any questions? Yes?
Where did you get the 0.72,
I'm sorry?
the value of F?
Where?
Because the graph from chapter 6 doesn't go.
It should be somewhere in chapter 10. The exact location, I don't know. but that value is 0.72 for torsion, according to your book. So it should be somewhere in chapter 10. I don't exactly remember where, but that's 0.72 for torsion. Anything else? Okay, let's take a look at a design problem. Now, in design problems, you may have to assume a lot of things. Not just the value for C, but sometimes more than that. For example, a wire diameter, if nothing is given. Sometimes you have some clues. For example, if a compression spring is to fit inside of a hole, then obviously its outer diameter must be smaller than that of a hole by some small margin. And so that gives you a clue as to what the outer diameter should be. So you may not have to do anything with that. But sometimes, in fact most of the time, not only do you have to assume some dimensions, you have to pick the material as well. I don't tell you what to use. You can use steel, you can use whatever you like. So that, of course, is not something that I'm going to ask you to do, because that requires some experience in designing springs before you can do something like that. So if in the final there is a design problem on springs, then you will be told what to assume so that all of you will solve the same problem. Otherwise, you'd be solving different problems, all of which could be right. In design, there really is no right and wrong. There's cheap and expensive, but there's no right and wrong. So long as you satisfy all of your conditions, from a technical point of view, that's a good design. Now, it may cost a lot, and may be impossible to do, but from a technical point of view, it's okay. So let's take a look at this design problem. A camshaft rotates at 650 RPM, causing a follower to raise and lower once per revolution. The follower is to be held against the cam by a helical compression spring with a force that varies between 300 and 600 newtons, as the spring varies over a range of 25 millimeters. The ends are to be square than ground. The material is to be shot peen chrome vanadium steel valve spring wire, ASTM A232, with fatigue strength properties as represented in figure 1216. Now, that's 1216 of the book where I took this from. We'll do our own fatigue strengths. Presetting is to be used, determining a suitable combination of D, that D is the wire diameter, big D mean coil diameter, number of coils, and the free length. Include in the solution a check for possible buckling and surge. So the load on the spring varies from 300 to 600. And you should read the problem very carefully, because they give you, in most cases, a lot of good information, of course, but sometimes they give you something outright. For example, in this problem, if you read it, table in the book, you're free to do that. In order to find the force at solid height, to make sure that it doesn't yield the spring, what we need to do is find out what force is required to take the spring to solid height. In other words, how much deflection, and what is the spring constant or the spring rate. So this is what we're going to do. We have found the solid length. This is the solid length. You have this spring, and that's more or less the solid length of the spring. Okay? All coils are in contact with one another. What I would like to find out is what force is required to bring this to solid length. And then use that force to find the stress. That force is equal to the spring constant multiplied by this deflection. So that's what we're doing here. So they give you the free length as 1.25. You've calculated the solid length at 0.67. So the deflection at solid height, delta S, is equal to the free length minus the solid length, or 0.58 approximately. The solid force is equal to K delta S, where K is calculated according to the equation that we came up with last time. This is in terms of the two diameters. That's in terms of the spring index. They're both exactly the same. For steels, that's the value of the modulus of rigidity, 11.5 times 10 to the 6. So we calculate K. We have everything here. We calculate K, 5.1. And then you multiply that by the deflection at solid height, which we just calculated, and you find a force of approximately 3 pounds is required to take this spring to its solid height. And now you're in a position to calculate what stress that force produces. So there's the force, K delta S, about 3 pounds. Tau max at solid height, Kw 8 FSD divided by pi d cubed. Again, you have all of these values. You get approximately 47,000 psi. Has it yielded? Well, we have to find the yield strength. There's the tensile strength of the material. According to the equation we talked about last time, the values of A and M are found from the tables, and they are functions of the particular material that you have. That comes out to be 311 KSI. We're taking the yield strength of the material, 0.4 SUT. Reason why I'm taking it approximately equal to 0.4 SUT is that that's a good mid value. Remember, SSY changes between 0.3 and 0.52 or something like that. So 0.4, 0.45, you may see your book using 0.45. If not specifically mentioned what to use, I suppose you could use any value between 0.35 and 0.52, I believe. However, in the exam, should something like this arrive, I will tell you what to use so that you all will have the same value. That's not something you're going to decide. So that's a yield strength. And that's my shear stress. Divide the two. I have a factor of safety of 2.6 against yielding. Now, the second part of the problem says B, for dynamic conditions with P min equal to 0.9 pounds, P max equal to 2.9 pounds, will the spring experience torsional endurance limit fatigue? In other words, will it have infinite life? Or will it have a specified life? In this case, they specify 50 times 10 to the 3 cycles. But I've done it for both, so you can see both of them. Torsional yielding, static yielding, or torsional fatigue failure. In other words, lack of infinite life. So in order to calculate those, we need to come up with FA and FM. As you can see, the load in a spring, before we do that, we have to check buckling. It's a good thing I turned the page. I've almost forgotten about that. But let me finish what I was talking about, then we'll go to buckling. As you can see, the load in the spring, they say, changes between 2.9 and 0.9. In springs that are functioning between two solid parts or flat plates, this is almost always the case. You do not want the force on the spring to go to 0, because if it does, that means it's just loose and it's going to start walking around. In order for it to stay in put, you either have to secure it, however you may, or make sure that the load on it never goes to zero. In other words, it is very similar to what we did with bolts. There is a preload. However, in the springs, the preload is not as critical as it is in bolts. In springs, it's just to keep it in place so that it doesn't walk away. That's all. Therefore, when we calculate the alternating and mean forces, we do it this way. For example, in this case, that's what we have, with this being 0.9 and that being 2. Oh, not sigma. This is force actually, not stress. And 2.9, that's in pounds, not kips, pounds. So there's my mean stress. And there's my alternating stress. And we do not worry about the preload. We will start our load line from 0, 0, rather than from some obscure location. So on this spring, check buckling. So long as we have the free length. Once you have the free length, that's when you should check buckling. So alpha LO over D. Alpha is the end condition between flat parallel plates, so it's 0.5. Free length of the spring, 1.25. Mean coil diameter, outer diameter minus 1 wire diameter. 1.58 is less than 2.63, therefore there is no buckling. The alternating value of the load is 1 pound, mean value 1.9. Calculate the alternating shear stress. Again, everything in this equation is known, 15.7, and the mean 29.8. Once you have those, you can draw the load line. Now you need the strength values to be able to draw the strength line. Here, it's a good thing I didn't erase this. Here I've taken my SSE equal to 0.9 times 45. This is what I've used. I've used unpeened wire, and because I think it says unpeened wire
In the problem description.
in the problem specified. Well, it should say whether it's peened wire or not, otherwise, because they differ by a large margin. So it should state that. It says unpeened wire, so that's what I'm going to use, 45 KSI. The 0.9 that you see there is probability of survival. That's what they want. So I multiply that by 0.9. You can increase, you can introduce your factor from the table as well. SSU, 67% of SUT, we just talked about that, 208. So there's your Goodman line. This is 40.5 for SSE. SSU, there's the Goodman line, 10 to the 6. SSA and SSM are found using these equations. This is the equation of the Goodman line, that line. And again, SSA and SSM are coordinates of points of intersection. And this is the equation of the load line. You have 1 point on the load line. The alternating value of the shear stress is 15.7. The mean value is 29.8. Solve those two equations together to get SSA 29.6 and divide by tau A to get the factor of safety for infinite life. So this is okay actually for infinite life. But since they specifically ask for a life of 5 times 10 to the 3, let's take a look at that as well. And then there's a point to be made on some of the strength values too. We say torsional yielding should not occur because the material does not yield at solid height. Remember, we calculated its stress at solid height. Therefore, if it doesn't yield by the time you take it to solid height, it's not going to yield under the maximum load because the maximum load is smaller than the solid height. Which brings me to this point. I want to make sure I don't remember 67%, not 70, 67% of SUT, and it's a good thing I checked. So that's one point we need, let's say, for the Goodman diagram. There's another point here, endurance limit in shear. Endurance limit of the material in shear, SSE. Your book gives you some data and an equation to use in order to find SSE, the endurance limit in shear. This is on page 528. Let me just write these here from the book. It says SSA equals 35 KSI, which is 241 MPa. SSM equals 55 KSI, which is 379 MPa. This is for unpeened wire. We talked about shot peening here, right?
Yeah.
You bombard the surface of the spring and all of that to make it more resisting in fatigue. And then SSA equals 57.5 KSI, or 398 MPa, and SSM equals 77.5 KSI and 534 MPa. This is for peened wire. Now what these are the coordinates of the point of intersection of the load line and the strength line, which you then use to find SSE depending on the failure theory that you're using. Whether you're using Goodman or Soderberg, or not, you usually don't use Soderberg. You use either Goodman or Gerber. So this is what they give you. This is tau M. This is tau A. They give you this point, which is SSM and SSA. What we would like to find is the endurance limit. And in this case, that depends on the theory of failure that you use. In other words, and showing it just graphically, if this is SSU, for Goodman, I connect from here to here and continue until I cross that line, and that's my SSE according to Goodman. If I want to use Gerber, That's according to Gerber. So depending on which theory of failure you want to use, these will change. These numbers should not be too far away from one another as you do your calculations. In the absence of any of this data, if you're just trying to find some approximate value to solve a problem with, then use these values. So I'll write approximations. SSE equals 45 KSI or 310 MPa. This is for unpeened. And SSE equals 67.5 KSI or 465 MPa for peen wire. So those are just approximate numbers to use in the absence of anything else.
So what exactly is peen here? Is it the material of the spring itself?
What is peened? The wire.
They peen the wire?
Sure. Remember that the maximum stress occurs in the wire, right?
I was just thinking, how would they be shooting it at such a thin material?
Before they form the wire.
Before they form the wire. No, you have a wire, you peen it, you run it. It's very difficult to do it otherwise. I don't know, maybe somebody does it that way, but I doubt it. Okay, anything else?
You must have said it already. What material exactly was that? Are those values for?
Your book tells you exactly, and let me read from that. This is called the Zimmerli data. Suggests that it may be because of the original Unpeened springs were tested from a minimum torsional stress of 20 psi. Actually, they don't tell you unless they tell you someplace else. These are steel, however. These are all steel. And approximate values according to Zimmerli, and all of this comes from experiment. There's no way to prove any of that. It's just experimental data giving you that 1 point. So once we have that, then we have that SSE, one way or the other. Whether with that or with this, we have the SSE, and then we are where we used to be with all fatigue problems. We have a strength line. We have the mean and alternating values of the stress. You plot your point and draw your lot line. And the rest is exactly the same as before, with no change. We'll demonstrate that in an example problem, of course. Any questions? Okay, let's take a look at this example problem. Here's the problem. A helical compression, this is of course in your handout. A helical compression spring has 14 active coils, a free length of 1.25 inches, and an outside diameter of 7/16 of an inch. The ends of the spring are squared and ground, and the end plates are constrained to be parallel. This is for your, both for your surge and buckling. The material is music wire with presetting. The wire diameter is fixed at 0.042 inches. For static conditions, compute the spring rate, the solid length, the stress when the spring is compressed to the solid length, and will static yielding occur while bringing the spring to its solid length? So what we need to do is find what force is required to take the spring to solid length, take it to solid length, find a stress then, and compare it with the yield strength of the material. The spring index is d over d, mean coil diameter divided by the wire diameter. Mean coil diameter is the outside diameter minus 1 wire diameter divided by d, 9.4. The Ks and Kw, you recall this as the shear stress correction factor. We don't use that, we straight use Kw. The reason why it's in here is that in some books, and including yours previously, they use Ks for mean stress and Kw for alternating stress. We're just going to use either Kw or Kb for both and not worry about that. So just Kw is what's important here. So that's 0.154. Takes care of Ks as well, of course. Notice that it says the spring has 14 active coils, so Na is 14. Squared and ground end, so 1 dead coil at each end. So we get 16 total coils. Now, and to find the solid height, you can refer to the table that's in your book, and it requires a little bit of calculation, bringing in the pitch and whatnot. However, I believe that you'll be close enough by just saying the solid length is equal to the total number of coils multiplied by 1 wire diameter. This is not always exactly correct. Sometimes you may be off by 1 wire diameter. But for ease of calculation, to my mind, this is the best way of doing it. So I suggest that you do it this way if you want to use the